your final exam, I don't have it on here. It's whatever, universities do this big hairy deal where they're like, they come up with the final exam schedule, and I'm not sure. I haven't looked. It's out there somewhere. Is it May 8th? Okay, May 8th for an hour and a half. Like I said, I'm going to have to secure 5 computers somewhere. So, okay. Autumn said something that's like haunted me. She's like, "What'd you say?" It's like,
learning makes me sad.
Learning makes me sad. I'm like, oh my gosh. Yeah, I hear ya.
You said 30?
Learning makes me sad. I pushed out on Twitter the water footprint survey, so. Well, we're back to actually kind of looking a little more. If you take a chemistry class, one of the things I want you to know is solution concentration, or a little bit about solutions. In solutions, we talked about something called mixtures. Remember we talked about mixtures? We said a mixture could be homogeneous or heterogeneous. So the word is homogeneous. So what does a homogeneous mixture mean?
It's the same.
It's the same throughout. It's well mixed. Yep. So if somebody says I have a solution here, then it's probably swimming around a liquid, most likely, and they basically have 2 or more things that are swimming around in there and it's well mixed. That's a solution. We talk in terms of a solvent and a solute when we talk about solutions. The solvent is there in greater amounts, and the solute is the thing sprinkled in. Solute is in lesser amount, solvent is in greater amount. The solutes can be a solid, they can be a liquid, or they can be a gas. So like for instance, if you take your pop, a can of pop, or a can of Red Bull, okay, it's got water is kind of the matrix, that's the solvent. It's got sugar in it, that's a solute. It's got flavor in it, it's got caffeine in it, those are all solutes. And they're homogeneously mixed. So when water is the solvent, then your solution is an aqueous solution. So aqueous solutions basically have mostly water with little solutes added to it. So Red Bull is an aqueous solution. Pop is an aqueous solution. What I started to say is that carbonated? Is Red Bull carbonated?
There's 4 or 5 kinds of sugar out there.
There's what?
4 or 5 kinds of sugar.
4 or 5 kinds of different sugar?
Yeah, sugar.
All those oses.
Caffeine.
Energy.
Well,
Wait, is that Red Bull?
Yeah.
but my point was going to be is pop, and maybe you're not Red Bull, but pop has actually gas is a solute. So that works. Okay. So let's talk numbers. One of the things we talked about, I think, is parts per 100, always also known as percent. Parts per 1 million, ppm, parts per 1 billion, ppb. So this simply says, and I think I'm going to eventually go around the room, so let's go ahead and start with you, Autumn. If you have 20 grams of salt, NaCl, and 100 grams of water, what is the percent of NaCl? It is 20, because it's parts per 100, and you have 20 grams per 100 grams, you have 20%. Very good. So switching solutions now. Now parts per million is for stuff that's like trace amounts. But one of the ways that might help you is when you switch gears from parts per million to parts per billion with a B, actually you're talking about even less, even more even lower, okay? So, let's see, I don't think I have this in the form of a question, but if we were gonna, well, yeah, I can ask in the form of a question. So, Natalie, tell me what 1 million is. Like, yeah, right number. 1 million. I do 1.
1, 0, 0, 0, 0, 0.
Yep, that's 1 million. Yep. Very good. So actually what you're going to see here in a minute though is, can you help me out, Billy? Go ahead and pack that up into scientific notation. So that's 1 times 10 to the what? 6. Perfect. So 1 part per million could be like 1 gram of solute and 1 times 10 to the 6 grams of solution or water. You buy that 1 part per million. Well, the next ratio, I'll go back to you, Taylor. The next ratio is going to convert grams of solute to milligrams of solute. So help me out. 1 gram of solute is equal to how many milligrams? Milli. It's what? Nope. Nope. Yep, 1,000. Yep, 1 gram is equal to 1,000 milligrams. Yep. So if we slap that as our next term, 1,000 milligrams of solute over 1 gram of solute. We can do that. We haven't changed it or anything. All we've done is gotten the units different. So there, grams of solute cancel. We have milligrams of solute over grams of water. Now this one is less obvious, I think. I just left it because this is what your author did. But here is a beaker of water. So, so we're over to you, Glenna. And it is 1 liter. Do you remember the density of water? It's a nice straight number. How many grams per milliliter? I don't remember. 1? Yep, 1 gram per milliliter. So I'll still pick on you, Glenna. So how many milliliters in 1 liter? Oh, awesome. Okay, and I'm not even going to do it in the form of a problem necessarily. So I'll stop picking on you, Glenna, and I'm going to pick on you, Autumn. So if the density of water is 1 gram per milliliter, we have 1,000 milliliters. So how many grams do we have here? 1,000. We have 1,000. Exactly. 1,000 grams in 1 liter of water. Yep. So before we leave this, and we don't need this for this problem, but what do you think, Natalie? 1,000 grams of water, or 1,000 grams of anything, is equal to how many kilograms? One. Yep. 1,000 grams equal to 1 kilogram. Now, the reason I did all that was what we're at right now is, let's see, grams of solute cancel. We have milligrams of solute per kilogram, per gram of water. So the next thing you're going to see is that we are going to substitute in 1,000 grams of water and 1 liter of water based upon the density of water. Water, 1,000 grams for 1 liter based upon its density. So we'll go back to you, Billy. So, what would the units of this number be? Milligrams over liters, exactly. And as it turns out, your million, your 10 to the 6th, actually cancels. You have it in the numerator and the denominator, so those numbers actually cancel too. So 1 part per million, the concentration is the same thing as 1 milligram per liter. Which can be helpful because sometimes you'll hear people throw things at you, well, that was so many milligrams per liter. That's the same thing as parts per million. So tuck that one away. And we're going to do a similar one here. We're switching from 1 to 2 here. And so I think we're over to you, Taylor. So kind of like what Natalie did, what is 1 billion parts per billion? So what's the number 1 billion? Yep, 1 times 10 to the 9th. So 1 with 3 sets of 0. Yep, that's 1 billion. So we could say, if it's 2 parts per billion, it's 2 grams of, in this case, Hg. So help me out, Glenna. What element is Hg? Nope. First letter M.
It's in your fish.
Oh, it's bad in your fish. Yeah, so for your final exam, you can have your periodic tables.
Mercury.
Mercury. Hg is mercury. Perfect. So that's why, putting together the whole 10 to the 9th is 1 billion. So we could say parts per billion in terms of mercury, if it's 2 parts per billion, you have 2 grams of Hg over 1 times 10 to the 9th grams of water. Cool. Then, okay. What I do next on my builds is to, I think we're up to the autumn. What if I'll just show you. I'm going to go ahead and divide both the 2 and the 1 times 10 to the 1 times 10 to the 9. I'm going to divide those by 10 to the 6th. So what happens if you take 1 times 10 to the 9 and you divide by 10 to the 6th? And then double.
10 to the 3rd.
10 to the 3rd, yes, that was what I was after. Yep, exactly. And I'll kind of show you why I'm kind of doing this. Your author kind of went this route, so I'm like, oh, I can do that. So all we did with the numerator and the denominator was divide by 10 to the 6th. So now we have 2 times 10 to the negative 6 grams of the solute, Hg, over 1 times 10 to the 3rd grams of H2O. So we kind of come full circle. So of course this is 1,000, right? So Natalie, 1,000 grams of water, how many liters is that? 1, that's right. Very good. So that's going to be 1 liter here, 1 liter H2O. And then I'll go back to you, Billy. Do you remember the prefix? We said milli is 10 to the negative 3rd. What prefix is 10 to the negative 6th? That also starts with the letter M. Do you remember? No? Okay. That's fine. It's micro. So here now, and the symbol for micro is that kind of U-looking thing. That U-looking thing which has an extra tail on the front, that is actually the Greek letter mu. That U is the Greek letter mu. And it stands for micro, and that's 10 to the negative 6th, or 1 millionth of.
Why did you divide by 10 to the negative 6 on both sides?
Just to get it in a form where I could use the prefix micro. Oh, yep. She asked, why did I do this third thing here? Why did I go ahead and divide both the numerator and the denominator by 10 to the negative 6? And that was just to get it to this.
Why did you want something?
Because, that's a good question too. The whole micrograms per liter It's kind of like milligrams per liter in that, like, if you're working with environmental samples, especially, or quality control samples, they will sometimes slip into the micrograms or milligrams per liter. Yep. Just so you know. Actually, I think some of like the EPA limits might be micrograms per liter. What does that mean? Well, now we know that anytime they say micrograms per liter, it's the same thing as parts per billion. Anytime they say milligrams per liter, it's the same thing as parts per million. Same thing, lockstep. Just, so you might want to take this to you, have this handy for your next test. I don't know. However you want to do it. Okay, so let's see what we can do with this one. And I did work this out ahead of time. Kind of. Sorry, are we ready for you? Okay, so I like drawing pictures, and I tell my students, sometimes I draw pictures to stall. Sometimes I draw pictures because I can and I don't use the picture. Sometimes I draw pictures just because it makes me feel like I'm more in control. So we'll draw a picture. And it looks like this. I'm going to go ahead and use an Erlenmeyer flask. Okay. It says I have 5 liters of water. And I'm going to dump to that. Maybe an easier way to work this in my account. Let's see. I'm going to dump to that 80 micrograms of mercury. Oh dear. Hg. And we're supposed to knock out parts per million and parts per billion. Well, I've got it worked, but I'm trying to think. Just eyeballing this, and again, I've got it worked out, but can you use, I'm talking to Taylor, can you use what we just talked about? Let's start with parts per million. 80 divided by what? I don't think so. She said we're going to do 80 micrograms divided by 5 liters. Oh, wait a minute. That will give us, what will that give us? Parts per million or parts per billion? Parts per billion. I'm liking that. So, Glenna, do you have your calculator handy or phone handy?
I'm doing 80 divided by 5, that's
Right.
16.
16? Okay. So, micrograms per liter, and you're telling me, and I agree, micrograms per liter are the same thing as parts per billion. Okay, Autumn, can you help me out? How are we going to get to parts per million from that?
Okay, you have to divide both those by 10 million.
Well, one thing to think about it is just a little bit ago, you guys told me this was 1 million and this is 1 billion. So it wouldn't be 6. Right. So they're different by a 10 to the 3rd, right? But now which way are we going to go? So when I knock out parts per billion, excuse me, we have billion. Will that, and I'll ask it this one time, is this number parts per million be higher or lower? It should be higher. Wait, no, it should be lower. Oh gosh, parts per billion.
Should be a higher.
Yeah, it should be a higher number. Yeah.
So positive.
Yes. Okay. So I'm just thinking through all this, and my other classes I'm all hardcore about, you know. But it should be higher by a factor of 10 to the 3rd. That's right.
Yeah.
Yeah. So kind of like what you're saying, parts per million would be 116 times 10 to the 3rd. So Natalie, what's 16 times 10 to the 3rd?
I don't know.
Well, can you just in your mind, like, what is, or, nope, okay. What's that? Yeah, 16 with 3 zeros. Yep, that was my only point. Just 2 with 3 zeros. They be put on the spot.
That'd be 16,000,
Oh, it'd be milligrams per liter. Yep, milligrams per liter, yep. Yep, you guys got it. Good job. Okay, so I looked it up, and I'll go ahead and take it out here. Because this follow-up question, so this would be back to you, Billy. If this from the internet is the acceptable limit, come on, dude. Have we exceeded it? Goodness gracious. What is it, Monday? Okay, so what do you think? Do we agree with Billy? Go back. Oh, evil. Goodness gracious. Fixing to pull it. If it would stay long enough for you to see it, that would help. Okay, so we're at 16 parts per billion. What's that?
Just 2. We're way above it.
We're way above it. Yeah. I think this number should have been smaller.
You have parts per million, that's parts per billion.
Yeah, yeah.
So it's different. Yeah, but that was, the 16 was per billion.
Oh, I think we went the wrong direction. I got all excited here. This part with autumn, I did wrong. And I can see it from here because look,
So then
They're
doing
doing-
0.0016.
they're doing 2 parts per million is equal to, sorry, 0.002 parts per million is equal to 2 parts per million.
So we went
So
the wrong direction.
we went the wrong direction.
That should be the negative.
It was what you said at first. It's what Autumn said at first. This is what I get for not going with my notes. Okay, I can fix this. Yeah. Okay, I'm gonna put a negative there. And then somebody just help me out. What does, if I take 16 times 10 to the negative third, what do I get?
0.096.
Yep. And that would be parts per million. And that would also be 0.016 milligrams per liter. Final answer. Sorry about that, guys. So what do you think?
We're still bad.
We're still bad. What do you think, Billy? Yeah.
That was 19 what?
What year was it?
74. That's at the top of the bottom.
74.
Something about those 2. Ours was above it when we're 0.016 of it.
Yeah, 0.002.
There's an
extra
extra
zero.
0.
Mhm.
We are 1. Where is it? I see. On this.
Oh, 1992, yeah. So they reviewed it, and unlike our, what are the standards that, I cannot believe those, cafe standards? Oh my gosh, don't get me started. But unlike that, yeah, they, upon review, scientists found that they kept the same limit, looks like. Good job. Okay, what else we got? Oh, molarity. So yesterday, was that yesterday? Oh my gosh, seems like so long ago. You guys came up with the HCO3 minus, the molar concentration, and the Cl minus, the chloride ion concentration, in terms of molarity. So it's just a way to say how concentrated the solution is, and we use it all the time. And molarity, anytime you see that, that means moles of the solute per liter of the solution. That's it. That's all it means. Moles of the solute per liter of solution. So we use brackets. The word is brackets. It's funny because in my intro chem class, I don't use brackets, but I know I do my general chemistry class. So brackets, anytime you see brackets around something, they're talking about the molar concentration. We're going to be talking more about this coming up, but the one thing about sodium chloride, NaCl, is it will dissolve in water and it will break apart to give you Na+, sodium cation, and the chloride anion. And all this is saying is that if you have a 1.0 molar solution of that, 1.0 molar solution, and you let it break apart, this breaking apart, sometimes they call it dissolving. You could call it ionization. You could call it dissociation. All three of those words means it breaks apart. And notice that for every 1 unit of NaCl, you get 1 unit of Na plus and 1 unit of Cl minus. So that's to say, once it breaks apart, your molar concentration of your Na plus is also 1 molar, and so is your chloride ion or Cl minus. So that's all it's saying. 1.0 here and 1.0 here. Okay. Who was it that said the shape of this bottle looks like a perfume bottle? I don't know if you can see it, but she's in the lab yesterday. The couple of solutions you used were in those bottles with long necks. Those are called volumetric flasks. So this is a volumetric flask. And I might have mentioned before, volumetric flasks just have one gradation at the top. So she's trying to make up a 1.0 molar solution of NaCl. To do it, she needs to basically have 1.0 moles of NaCl in 1 liter of solution. We're kind of backtracking. You're like, well, how do I know to get 1 mole? Like, oh. So this is one of the things we've done before. We use the periodic table. And actually, let's go ahead and do it this way. I don't know if I'm getting. We need 1 mole of NaCl because somebody told her to make it out 1 liter of solution. So who did we leave with? Who's the next person to pick on? I think it's Natalie. So using a periodic table, help me out. What's the decimal number for sodium?
Is it the number in the corner?
It's the not the one. It's the one that has decimals, so it's not the whole number. It's the decimal number. Yep, 22.9. Okay, and then back to you, Billy. What's the decimal number for chlorine?
Let's see.
You know, periodic table with you. You're in chemistry and context. Well, I'll tell you, and then do you have a calculator? I'll tell you, then you knock it out.
35.45.
35.45. I thought you had. Everyone has a periodic table. Okay, so can you add this up for me, please? You know who you are, Taylor. All right, Brain Man. Okay. Brain Man. 58.35. And I'm just going to kind of remind you what maybe we've done before is that is a good units to, it can either be how much it weighs in U's or atomic mass units, or it can be the molar mass. And actually, I'm going to go with the grams per mole version of that number. It's the grams per mole. So, Glennon, if we want 1 mole, how much grams do we need to weigh out sodium chloride? Yeah. Yeah. Autumn, if we want 2 moles, how much do we have to weigh? Just how much bigger? If we want 2 moles of this, how many grams do we have? Twice that. Another point. Yep. So in the top or in the numerator of this molarity, moles per liter, I'm going to go ahead and just put the molar mass we came up with. Notice I've got it just looks like they use different numbers here. I know we can't, and I like the number, 58.35, they have 58.5. I don't know, but that's where their number came from. So we'll go with their number. We can go find something. 58.5 grams. We got that using the molar mass of sodium chloride from the periodic table. All right, so that's what we're going to weigh out. And this says, be careful that you don't get your water first. You don't get your 1 liter of solvent first and then add your sodium chloride, your solute, because then your solute is going to displace some of your water. You're going to have too much liquid. That's all it says. So talking you through it, it says empty. My first word over under 1 is empty. Okay, so you get your volumetric flask, affectionately called vol flask, and it's empty. You put your sodium chloride down there, and then you add about half of the water to get to a liter. The reason for that is so you have shaken room, because some things dissolve quickly, some things don't. Okay, so you got shaken room. You dissolve all your solid, and then you add enough water to bring it up to the mark. Mark's the right word. And then I want to emphasize number 4, because it's gotten all of us before. So basically what you did was you had kind of a more concentrated solution down here. You topped it off with water to the mark on your neck. And by golly, if you don't mix that thing, the problem is when you go to use it, or somebody goes to use it, you made it for, they're going to start pouring off the top. And what will be wrong with that? There's no solute in it. It's like just all pure water. Yeah, because it wasn't mixed. So you have to invert it a few times. Okay, that's it. So, I don't think this isn't your turn though, is it? It's coming up. We have a problem here. And again, I think a picture's nice. On tests, I mean, usually when you take a test, my test, I have plenty of time to just stop. Ugly looking beaker. So, I have 95.0 milliliters of water. And I'm going to add 5.0 grams of NaOH. So who did I last sleep with?
Is it autumn?
I did autumn?
Yeah.
Okay, so I'm ready for Natalie?
No? Oh, maybe that's another time.
Nice try, Glenna. Okay.
What's question?
Okay, Glenna. Awesome. So based upon what we talked about before, and it's also up there, I'm going to say the density, and that's just the symbol for density, it looks like a P, but the density for water is 1, and you actually, I think, answered that before. So if that's the case, how many grams do we have here? 1 gram per milliliter. Yep. That's 95.0 grams. Perfect. It's just wonderful waters like that. Like, are you serious? Yeah. So we're supposed to come up with the mass percent here. So, what's that?
Is that how you got?
It probably is. It's
Okay.
kind of like a circular thing almost. So we are going to take the 5 grams that we added and divide by the total mass of the mixture. So Autumn, what is the total mass of the mixture here?
100.
It is 100. That was my point. It's 5 plus 95. 5.0 plus 95.0. It's 100 grams. So Natalie, you don't have your calculator, you have your phone.
Yep, if there's nothing I'm struggling
So what's 5 divided by 100?
with. 0.05.
Right, and then multiply by 100 to get parts per 100. It is 5. Yep. So it's 5%. 5.0%. That's it. Very good. Okay. Well, we need to kind of mix it up a little bit. So now we're supposed to knock out what is this solution, the same solution in molarity. So who are we ready for? Bill. Bill Lee, excuse me. So do you see where, well, let's do it. Here's my big M. So Billy, what is that a ratio? Molarity. It's a ratio of what to what? Yep, moles to liters. Yep. In this case, moles of NaOH to liters of solution. Cool. So, over to you, Taylor. How do we get from grams to moles? That could be, but what I'm after is like the periodic table. How do we use the periodic table to go from 5.0 grams is equal to how many moles? Nope.
Wait, that's 1 mole.
We're going to have to use the periodic table. That's your hint. Here, I'll ask you a different question. Help me out. What's the decimal number for sodium?
22.9.
22.9? Okay. What's the decimal number for oxygen?
15.
I got 16.00 for oxygen. 15.999? Okay. Okay, and then decimal number for hydrogen?
1.0.
Okay. So, and this is one of my favorite numbers. So,
22.9 is?
no. What is these added together?
I was like,
Is it 23 and this one?
39.907.
39.907. Well, that's not, but okay, 39.907. That's.
Is your favorite number 40?
It is 40. We'll go with that. 39.907. How'd you guess? Okay, so that's grams per mole. Okay. Now don't lose sight of what we did.
On paper it's 16. They must have rounded that 15.99. 16.
Okay. Okay.
That's it. There it is. And they have for the hydrogen, they have it for 1.01.
Okay. Okay.
Oh, there it is.
Thank you. So Autumn, what do you think? Is this this is the grams per mole? Oh, I guess that won't work. Let's just see what we got. Yeah, they got 40, which is close.
This is nice.
Yes.
What were you asking me before?
I was asking you the 5.0 grams of NaOH that we added. How can we say how many moles we added? And then this was kind of how we do it. In order to know how many moles in that 5 grams, we have to use the periodic table to get to the molar mass, to get to the moles. That was the question I was asking. And there's you did fine. Well, let's finish up. So in the numerator, well, I don't know how to ask this in the formal question. I'll just put it this way. And again, instead of the 39.907, we're going with 40.00 as the molar mass for NaOH. If we want to get to moles, we can get to moles if we take 5.00 grams and if we divide it by the molar mass, 40.00. How does that work? Well, if you're dividing, it's kind of flipped, and the units of grams cancel, you're left with units of moles. Not my favorite way to do this, but I think that works. So Autumn, in the form of a question, I can't remember how this is going to work. but we don't have liters. We need volume down here. What sort of volume do we have over here in our problem?
We have a liter or more.
We have, but I can't answer in the form of a question. We're going with 95 milliliters, which is, that's wrong, isn't it? No, yeah, 95 milliliters, which is 0.095 liters. Yeah, that's kind of crazy. So 95 milliliters. 95 milliliters. I'll ask this in a formal question, Autumn, because I've seen you do this before. Help me out. How do I get to liters from milliliters?
1,000 on the bottom
Yep,
over 1.
yep. So do you see where that bottom number came from this? If you take 95 divided by 1,000, you get 0.095 liters. Kind of ugly people. So we're all set up to do part 4 on Friday then, right? That's all I got.
This stuff is complicated.
It was, but at least it didn't make you sad, or did it?
It's helpful to break it down.
Yeah. I tell people, like, chemistry has the pretty part or the ugly part, and then it has the number part, which, you know.
I took it because I fear biology.
Because you what?
Fear biology.
You fear biology.
More than chemistry?